Hello, this is the fourth video of our series of how to use the LVMDAP. In this video, I'm going to show you or to explain you how the basic code of the basic script of the local volume mapper DAP works. We have seen it working the other day. For make it work, you just need to run this command. If it's the script is lvmdap-conf. If you type here -h, it's going to tell you what are the inputs that are expecting. Normally, it requires just the LVM file, that the one that we explained in the previous video. A label that is basically every output is going to be labeled with this string that you put in here, and the configuration file that is a YAML file that they will explain in another video. So it can also run with the output of the LVM simulator. So then you need to include this entry. And replacing this file for the LVM simulator file, or in a RC format that is a particular format I will explain, because it includes two extensions. It's a raw stack spectra plus the errors, but I will explain in another video. So for running the script, as I said to you the other day, you just need to run in this way with the LVNS frame, the label that you want to put, and the configuration file that you want to run. And then it's going through all the steps of the analysis that are described in the article. Okay, but this is not very illustrative. This is just like a black box. So instead of just running that in this way, to understand how it works, we have created a notebook. That notebook, it's let's see. It has the same name. It's in the notebook directory. It's lvmdap-conf. And in here, like in the script, it requires 3 entries. We're going to use different entries now, just to show you how to modify some of the required files. That basically is the LVM file, the file that I described the other day, the label, and the YAML file. And so we started that, and it started with certain definitions. Okay, input the required libraries that needs to the script to work. Define some functions, and the first thing that it does is to load the YAML file. This YAML file, you can use the one that we're using in the example before, but I want to modify that. We're going to use a different one that is more similar to the one that we use for running through all the LVM dataset. And this one is included in the Google Drive that I was pointing the other day. So I have just downloaded, and I open with my preferred editor, that is Emacs, but of course you can use the edit editor, and that's the other one. You can use the editor that you prefer. And in here, let's see, I'm going to enlarge that a little. So let's enlarge that. And in here, you see that you're going to see these entries that are pointing to local directories that you need to chain to make it run in your own installation and your own directories. Okay, so let's go back to the directory that I'm working in, using this directory here. And the examples, remember that I copy everything here. The output is going to be this other directory. So let's go to examples. I will explain the content of the YAML file in a separate video. I think it deserves a separate video. but some of the entries are easy to understand, like this one. This is the output path, is where all the output files are going to be stored. In this run, it's going to be in this way. The LVM dir is the directory where you install the code. So in this particular case, it's this other directory. Remember from my previous videos. So we just paste and copy here. Okay. And now it is going to ask for certain RCP libraries. And those I have included also, I have already downloaded. They are in the Google Drive. So you just go to the Google Drive and download them, and then you place them wherever you want. I just I was too lazy, so I copy those here. But I'm just going to copy the ones, exactly the ones that are in the sample from my own computer, just not to make big modifications. So we need this one, and in which directory they are, in this directory. So we change that. This is the RCP directory. Okay. So I put that here, and I put that here. Okay. And by now, that's all we need to modify. So what we need to modify basically is these input directories. I'm going to order that a little. It doesn't matter too much. So where the LVM DAP has been installed, the output directory, and where to find the raw stack spectrum. So we save that. Let's hope that didn't mess up with any other thing. So again, this is here. And now we are going to run the next cell. Okay, what is said is not finding the files. Yeah, okay, that's again, obviously because I didn't put uh, the entire path. So that should be here. Let's see. Now it works, and it shows you the content a more readable way of the YARN file. As I told you, that we are going to explain in another video. So, well, now it's going to start reading the LVM file, and let's see which file. Well, let's we'll settle in here. So next step is that it's going to read this file, and the file we are going to read, as I was telling the other day, it's the one that we have distributed in the it was here. Okay. So data, this is the helix nebula was LVM. I wanted to use the data we distributed for the helix nebula, but that's where I thought I have already downloaded. Let me look for that for a second. This was the example that we distribute. And where I install, where I copy that. I hope I didn't do it here. Nope. Okay, so wait a second. Okay, I thought that I had already copied that file, but I didn't. So let's copy from my local uh, disk. You can download from the web page, but it's going to be considerably slower doing that. So yeah, that's the file we want to analyze. Okay, so I go here, and obviously the path should change. So I need to write that. And well, if we proceed in this way, we are going to analyze the full. So now we need to name here, put the label here. So let's say helix. Okay, 10. I will explain you why I say 10. If I do in this way, or 5, sorry. If I do in this way, it's going to analyze the full helix nebula, and it's going to take a while. So I'm going to make a simple trick, and I'm going to rewrite the information in the YARN file, I mean the configuration file, just uncommenting that. This is just to fit the first 5 spectra or fibers in the LVMS frame. Okay, so this way is going to analyze only the first 5 fibers. That's going to be convenient for speed, no? So it's reading the information, showing the information. Now it's loading the feeds file to the an axis trim to 10 trim to 10. Why 10? Why a 10 and not 5? That's ah okay, I tricked myself because it was written here. Okay, you see, let's say 5 and it again. So it said that it's trimmed to 5 spectra. Okay, so now we apply the mask and create the error map. Now what it is going to do is to first step, it is going to create an integrated spectra. That what is doing here. Of course, this is not the integrated spectra of the full nebula, because we have just got the first 5 fibers. Maybe these are not the ones that have optimal signal to noise. We will try to do later with the full nebula. So it's creating an integrated spectra weighted by the errors. And using this spectra, the first thing that the LVMDAP does is to estimate the resif using matching the location of H alpha plus nitrogen. And that's exactly what's going on here. And it's making a match. And obviously, this is the problem when you are using just 5 fibers, that you may end up in a problem estimating the resif. So, but it's not that relevant, because it's found around 0. So, and this is around 0, so that's not going to be a big deal. Later we will show what happens when you have an signal to noise. Then we prepare the output files, and we feed the integrated spectrum. And now we find a problem. Let's see what's the problem. Yep, that's curious. Okay, so cannot find this file LBM in the legacy directory. That's something to do with the relative directories that we are using. Let's see why is that. Go no, LVMDAP. code LVM legacy. Okay, so it's pointing towards the directory, and then legacy is said that it cannot find this directory, but as you can see, the directory is there. I mean, the file is there. So it's something in the path of what we wrote in the jam file, or that's why is that? Said that it cannot find the legacy file. Okay, wait a second to see what it has been read here. Let's see. Yeah, it's the path somehow. It doesn't like the path. Okay, you know what was the issue? I need to update the notebook that I distribute. I always run the notebook in a directory where we have a subdirectory named legacy, where is all the configuration files. And apparently, this should be indicated to the script. So I have added the following line that I will add in the distribution, the following cell, that is this one. So it's changing the working directory to where you have the installation of the LVM, so LVMDAP. So you will have this a legacy subdirectory where it's basically included all the configuration files. So let's again load the LVM file. Now it created the integrated spectra. Now it looks for the receive, but it fails because there is no strong emission lines in here. Now it's preparing some of the output files, removing the existing ones and writing a new ones. Now it's starting to fit the integrated spectra with the recipe and the set of the emission lines, and that's where it crashed before. So now you can see in this cell what it's doing is first finding the non-linear parameters that I think they are fixed in this configuration file, but we need to check that. And then it's fitting to the RCCPs with a simple model. It has found that only one star is enough to fit the continuum. And now it's going through a loop for the different emission lines that are included in the configuration file to fit with Gaussians, and it's fitting them with Gaussian functions. And sorry, that has jumped to another cell. Again, my mouse is doing funny things. Okay, so this is the cell that we are exploring. And in this cell, there is fitting the H alpha with nitrogens, the sulfurs, and then it's fitting oxygen 3 with a H beta, then fitting, let's see which other lines are fitted, H gamma, H delta, the oxygen 1, the two oxygen 2s, and the two oxygen 3s in the near infrared. And then it removed this emission lines model, as explained in the first video, and then it fits again with the stellar population. Only fit the stellar population if there is a threshold about a certain signal to noise and a certain flux intensity. Then it's fit with the set of SCCPs. If this is not fulfilled, then it's looking for a single star that reproduce somehow this noisy stellar continuum. And this is the end of the fitting. So now it's saving the output of the results in certain files and that are indicated here with emission lines information and the RCCP information, the files for the coefficients and for the average of the stellar populations. And now it's going to plot the results of the fitting with this integrated spectra. That now it's integrated only on 5 fibers, so it's quite noisy. As you can see here, later we will do for all the fibers. And once it's done that, it's run the non-parametric analysis, subtracting the stellar continuum that is not very promising here because it's pretty noisy. And the emission lines also are not very intense because it's just, as I told you, the first 5 fibers. And it's going to extract the using the non-parametric method, the intensity of a set of emission lines. This is the list of emission lines that is included in configuration file. And it's also labeling if it's possibly blended or not. And just this is added in the output table, the possibility that this line is blended, so you can guess later on, figure out if this analysis is good enough for you, and if it's possibly blended, then maybe you have to take it with care, the results of non-parametric fitting. Now it's said that it's start fitting the full row stack spectra. So we remove the option of plotting. If not, we are going to get crazy showing the plot. Well, there are 5 spectra, but if you still for the 1700, then it's going to be a lot. And now it's going to repeat exactly the same thing that we had done for the integrated spectra. It's going to go spectra by spectra, and it's going to show you in here. That's why we have trimmed that to 5 spectra, because if not, it's going to take a lot. So it has already finished. So then rearrange the model for storing the model file. This is the output of the model file. So there are in the first 5 fibers, only 3 are signs. That's why the output model have this shape. This is the spectra, it's like a cube, or as I said in the first video, it's a cube where each slide is a row stack spectra, where the x-axis is the wavelength, the y-axis is the spectra that we are storing, either the original spectra and the different models it was in the first video, and the third dimension that here is this one, the second one, correspond to the number of fibers that you have analyzed, that in this case are 3. There is saving this file, creating some reading the tables of the analysis to create the DAP table. That's what is doing here. Rearranging the parametric emission line data products to be in a nice format for a table. This is this table here. You can visualize the different tables if you want later on by yourself. We extract the velocity, the average of velocity for the emission lines close to H alpha. And this is the mean velocity. This you see is around redshift 0. And now we create a model of the gas pure, subtracting the data to the model of the underlying continuum. And from them, we derive the non-parametric, we derive the properties of the emission lines using the non-parametric procedure. It's pretty fast because there are only just 3 spectra. We convert the non-parametric emission line data into an AstroPy table. Then we do the second analysis of the second parametric analysis of the emission lines. In here, fitting Gaussians to the same model that was used to derive the properties of the emission lines using the non-parametric. Now we do the parametrics. Remember, from the first talk, there are 2 analyses of the two parametric analysis. So now it's fitting all the lines for the spectra 0, 1, and 2, because there are only just 3 spectra once we have that, we store that in a AstroPy table. Now we're going to split the results from the non-parametric analysis in 3 tables for the blue, red, and I regimes of the spectrographs. As I told in my first talk, this was due just to the reason that we cannot store a table with more than 1,000 columns in fits table. We add the ID to all the tables. The ID is the identifier of the fibers, well, that's not relevant. And finally, we store everything in a single table, the DAP table. That we correct for the line of sight velocity distribution, the dispersion for the instrumental one, the dispersion measure for the emission lines, and create a value that is in kilometers per second. Okay, this is the table of values in kilometers per second, then we dump the final model that can be that normally is waived in the full analysis just for the sake of space, and we make an estimation of the chi-square of the model using all the stellar population and the emission lines using the model that we have created. That we store. That's a funny plot of how the chi-square of the different emission lines change across. That's the APY widget again. Well, it's not important to show this plot. Well, finally, that's around some plots that are not that relevant. This is the final thing that is important here, that I should remove from the distribute version those plots, because this is just for the sun analysis of the residuals that is not relevant in here. So that should be removed from the distribution. We store the result. That's the important thing. We store the DAP result, okay? We can see the content of this DAP file. In this DAP file, as I explained in my first talk, it's included different extensions, the header, the position table, the result of the analysis, the average parameters from derived for the stellar properties, the coefficients of the decomposition of the stellar component, the results of the analysis of the first analysis of the emission lines using the parametric method, 3 tables including the analysis of the non-parametric, the result of the analysis of the emission lines using the non-parametric method, the second analysis of the emission lines using the parametric, then we have the corrected a table including the corrections for the the corrections for the line of sight velocity in the instrumental one, a table with a chi-square of the emission lines to evaluate the quality, and also an extension of these are new extensions that I should explain in an upcoming video. And this is the info that basically correspond to the configuration file. So if we want to reproduce exactly the same analysis, you can use this input again. So, well, we can plot some of the results that we have produced. And, well, yeah, okay, my utils. Funny thing. Okay. Okay, let's remove that. That I need to include in here this search call. Let's make a pause here. Okay, it has not paused that. Okay, we need this simple tool that basically look for strings in the column names of an AstroPy table. I find it very useful for finding particular, when the tables are huge, to find the column that I want to plot or I want to analyze. Okay, so let's see if this works. So far, so good. So I'm going to add to the DAP table the table with the velocity dispersion. Okay. And now we can make some plots of, well, there are only 3 fibers. The plots are pretty idiotic, no? That will be a plot of the H alpha flags and the chi-square. But since there are only 3 fibers, and then you see very little from here. And we will be able to make other plots, but with 3 fibers, it's not a very good idea. So you can go cell by cell and see exactly what the code does, but all the structure of the LVM, the LVMDAP config file or script that is included in the article are included in here. Of course, there is a lot of subroutines in there and a lot of things that happen in the background. But all the structure is here, so you can play and visualize each step if you want. So what I'm going to do now is to rerun that, but just not including this, I'm commenting this line, and let's see if I have to comment again. So let's start again. So now we are going to fit all the spectra, okay? Okay, not needed. Okay, so since these are now all the spectra, it does not say here that the data are trimmed. Of course, it takes a bit more to create because it's loading all the spectra. Okay, now we mask this spectra and create an integrated spectra weighted by the errors, by the inverse of the errors, of course. And this is the one that we now analyze to look for the receive. Let's see if there's a difference with respect to what we saw before. Yeah, of course. Now there are signal, and there's the 2 nitrogens and the H alpha, and it's looking for the peak emissions. So now we have a better estimation of the residue, basically means zero. And now we reanalyze the integrated spectra. Now it's the analysis it's different than before. Now it has gone above the DER score where it produced a result for the non-parametric properties. It fits the mission lines, and now the decomposition of the stellar population, it's much more complex because now we have signal contrary to what happened before. Okay, so now that we have that, we can save the result and can plot. Before we have a lot of noisy spectra. Now let's see if it wants to be plot. Yep, that's let's see. Okay, yeah, that's because we use EP widgets at a certain moment. So this is the fitting is not very good because it's also very noisy. But for the measure lines, it's quite okay as expected. Maybe we can tune the parameters to produce a better fitting of the continuum. That's not relevant in this state, but it should be done. And now it's going to go through all the different steps, but obviously this is going to take a while. So what I'm going to do is to run all the cells and stop the video in here. Okay, so until it's saved and until it make the same plot as we did before. Okay, so and in a future video I'm going to start showing the results for this analysis. That's all.